Today's topic is one I'm pretty passionate about. There's a lot to talk about when it comes to Moldflow cooling analysis, and the title of today's is "What's Best for You." So our key message here, though, is no matter what type of analysis you do, the fundamentals really don't change. How do we take advantage, rather, of those fundamentals to get the cooling and uniformity and efficiency that we want? There are different types of Moldflow cooling analysis, and we'll get into those. But cooling design should not be an afterthought. Cooling uniformity and efficiency can be improved proactively, and we do that through simulation. So let's say we have a flat plate and we have two channels, and we see a 24-degree variation across the part. Maybe we add another channel in the center to cover that hot spot. Now we've got an 18-degree temperature variation across the part. Some improvement, but not quite where we'd like to be. So now we put 6 channels. Now we've got that temperature range down to 12. But the point is that the pitch, the distance between channels, controls that surface uniformity. And then we have the depth, the distance between the channel and the part itself, part surface itself. This is going to control our core and cavity differential. With poor depth, you see a temperature differential. With proper depth, you see that temperature differential go away. And it's not always going to be, right next to zero there, but you get as close as you can, right? So how do we improve cooling uniformity? Solution 1, add or move water. Solution 2 is to add higher conductivity inserts. Solution 3, maybe we go to conformal cooling. Conformal cooling is all the buzz these days, right? So we look at a conventional cooling design, and you can see right in this area here, we can't get these baffles real close to the surface. So, and it's also on both sides of the tool, core and cavity, it's difficult to follow the blade contours. So here's a conformal cooling design idea. You can see we have cooling lines to conform to the part surface geometry, particularly in the fan blade areas. We're able to reach the deep core areas a little easier than we could with the conventional cooling. We added cooling to cool the sprue. So we look at the results of conventional versus conformal. What I did in this case was ran the cooling time out until we got similar temperature results in both of the designs. So on the left, to get the temperatures where they are in this cross section took 90 seconds. And on the right, took 62 seconds. There's 191 up to 231 degrees as you go up the core here. That's a 40-degree variation. Here we've got a 4-degree variation. And now we're going to look at the cooling lines themselves. And 3 questions you really need to ask. Do I have turbulent flow? Are the cooling lines sized properly? And do I have proper circuiting? So let's look at a design where maybe we don't have turbulent flow. Turbulent flow is more efficient heat transfer. When coolant flows in a laminar fashion, it kind of sets up layers through the cooling line that are a barrier to heat transfer. With turbulent flow, it allows that heat to move, laterally across a cooling channel much more efficiently. So in this case, we've got laminar flow, very low Reynolds numbers. And for that, took 67 seconds to reach the temperatures that we wanted. And we get a relatively high temperature variation across that part. And then we looked at turbulent flow, moving that Reynolds number up to a much higher threshold. And for that, we were able to bring the cycle time down by 7 seconds with a lower temperature variation. So how does this impact cycle? So in the laminar case, took us 7 seconds to get to the temperatures we wanted on that. When we matched those temperatures with a condition where we were in the transition region between laminar and turbulent, we dropped that down to 5.8 seconds. And then when we went full turbulent, we were able to get it down to 4.9 seconds. It's, oftentimes you just don't have enough GPM available at your mold to be able to do, single in and out for every circuit, 134 GPM on that one. A lot of people put so many lines together, it doesn't require many GPM to get turbulent, but we had that temperature rise, right? But with proper circuiting, we got cooling uniformity and we were able to do it at a reasonable number of GPM. So, the topic of this webinar was what's best for you. And I would argue that all cooling analysis will give you some type of opportunity to improve. It's going to give you better parts. It's going to increase your profitability, right? And it doesn't matter what type you're doing, temperature uniformity and coolant flow efficiency are king. So how do we do that? How do we solve that problem? Just to reiterate, so for cooling uniformity, you can add or move water. You can change out steel for higher conductivity materials, or you could use conformal cooling. So, and that's not just a cooling uniformity thing. These things also lead to more efficiency. But the other side of that equation is you better make sure that the channels that you have turbulent flow, that you have sized them properly, and that you have circuited them properly. So here's some general ideas. So make sure you plan ahead to have Moldflow cooling analysis done proactively. And again, have this done at the earliest stages of product development. Here's some specific ideas for molders and OEMs. So insist on Moldflow cooling analysis. Do it yourself or use an outside source. We can help you in either case. Know your GPM and do the math. I mean, what does X seconds of cycle savings mean to you? For part designers, when you're designing your parts, avoid difficult to cool areas where you possibly can. And then, of course, use analysis to identify those areas. For mold makers, be creative and test different designs using analysis and use those cooling suggestions from analysis.